Hello everyone. Welcome to this year's lecture on quantum computing at the Leiden Institute of Advanced Computer Science. My name is Florian Neukert and I have the pleasure to introduce you to that very exciting field. And exciting it is because it has been in the news lately, but it has been in the news for good reason. The expectations that we have towards quantum computing are high. We expect quantum computers to help us solve some of the most interesting and most complicated problems that we have and that we cannot solve using classical computers. When I talk about classical computers, I mean these computers that we all know, the computers that are not quantum, like your laptop, like your desktop computer, or even supercomputers, the cloud. They're all classical computers. But quantum computers are different, and in this lecture we will learn about this difference, and we will see that quantum computers will not replace all the classical computers, they will augment classical computers. There is no need to do something with a quantum computer that a classical computer can already do pretty well. With quantum computers, we're really interested in solving these kind of problems that we cannot solve today and accessing complexity classes that we cannot access with today's computers, and we won't be able to access with future computers, future classical computers. But first things first, let me introduce myself. Florian Neukert, and I'm a director at the Volkswagen Group, and I'm responsible for a department doing applied research in the fields of machine learning, broader artificial intelligence, and also quantum computing. Before, I spent a couple of years in the United States, and I've been working as a principal scientist for artificial intelligence and quantum computing, also for Volkswagen Group. And before that, I did something else, also for Volkswagen Group. So you see, I spent quite some time at Volkswagen Group, almost 11 years by now, and it's still exciting. But my focus has always been applied research. And when I talk about applied research, I know this is somehow contradictory, but what I'm really interested in is researching applications or developing applications and do the research needed to implement these applications. So work on new stuff and do the research that helps us implement the new stuff. But let's talk about more interesting things about this lecture. So in the introduction, we will learn about the fundamentals of quantum computing. We will learn about what they can be used for, and we will revisit this topic. This is not something that we will only talk about today. So you'll see I have a very special style of doing lectures. So I will introduce certain topics, and then a couple of hours later, we will talk about it again in more detail. It's iterative. So I feel this is the most powerful way of introducing someone to a new topic if we learn about fundamentals and then revisit as we go, as we learn more and more specific topics. We'll talk about quantum computing architectures. So there is not only the one quantum computer, there are different kinds of architectures that we consider to be interesting today. So today we specifically look at quantum annealing systems, which are very suitable for solving optimization problems and sampling problems. And then we look at gate model chips or universal quantum computers. So these are the ones that we all want and that we all have been waiting for, but we're not quite there. So we have some small systems in place, but we cannot solve all these problems that we expect them to use for in the future today. We'll talk about classical bits and quantum bits. So classical bits, as you know, the smallest unit of information in information theory is the bit, and the bit can be 0 or 1, and it doesn't matter if you look at it or not. So if you do an operation on a bit string, you can always interrupt this operation, extract an intermediate result, and continue with your computation. That is not true for quantum computing. It's different. It even matters how you look at that bit. And looking can mean different things in terms of the quantum computer implementation. So it can be magnetic fields, can be firing polarized laser light, can be a couple of more things. And you see, the interesting thing with quantum bits and short qubits is that there is a direct connection to physics. So how we implement it directly in the device physics and read out from these devices, and so they behave somehow different. We'll talk about general features and some examples. So the first quantum algorithms that have been developed and that already showed some promise, even though back then we didn't have quantum computers to verify these algorithms. The theory was there, and we could talk about it already. And these are quantum teleportation and super dense coding. And now teleportation sounds very exciting, but unfortunately, it's not Star Trek. It's a particle statistical thing, so it's different. It's still exciting. And we talk about some more quantum algorithms that have been developed over time. So the classics, so to say, which are Deutsch's algorithm, Shor's algorithm, Bernstein-Vazirani. We'll talk about search with a quantum computer, so how you can do that and how we can show that this is a lot faster than with a classical computer. We'll talk about quantum error correction, and we'll solve some hands-on examples with a D-Wave quantum annealing solver and look at some more algorithms such as quantum artificial neural network if time allows for it. The prerequisites to this course are some basic knowledge about quantum physics, but fear not, we'll repeat everything and go through the quantum physics required for doing quantum computing. We'll talk about linear algebra, specifically finite dimensional vector spaces over complex numbers. That's something that we definitely need. And the Dirac notation, which is a different way of writing down um, matrix and vector operations. And we'll learn about that too. So there is no deep knowledge about quantum mechanics required for doing quantum computing. Why is that? So quantum computing with quantum physics with quantum field theory and all the other theories that we have for weak interaction, that we have for strong interaction, that we have for electromagnetism. So this is really complicated. And still, we don't need that for doing quantum computing. Quantum computing, as you will see, requires only a very small subset of quantum physics to develop algorithms. Of course, it depends. If you want to go into building quantum computers, the whole story is different, and you need to know a lot more. You also know a lot more about the device physics and electrical engineering. But talking from an algorithm perspective, and this is what we do in this course, or a software developer perspective, um, it's different. So we only need a very small subset. And why is that? So a quantum computer is an extremely simple physical system. It's discrete, not continuous, so we'll learn about that in a bit. And it's made up of a finite number of units, each of which is a two-state system, the simplest quantum mechanical system. And these units are the quantum bits, of course. And the difficult in quantum mechanics is to get a feeling for how the formalism can be applied to actual phenomena. Solving oversimplified abstract models of real physical systems to which the quantum formalism can be applied. Which are the relevant features and which are not? So that's the interesting question that we need to ask ourselves and we need to ask when we look at these systems. And quantum computing, in short, is dealing only with a very abstract model. It's the easy part of quantum physics, so to say. Again, I'm only talking about the application and developing applications. So given APIs are in place already that allow us to implement algorithms as we will learn about them in these lectures. So which is specifically in terms of stacking together gates for gate model chips or um, universal quantum computers, and preparing an upper triangular matrix for annealing systems. So there's a very specific way to how you can prepare um, a problem for a quantum annealing system, which is called an Ising spin model, and there's a mathematical equivalent which is called quadratic unconstrained binary optimization, and this is what we will learn to implement. And if you have an API that can take that and submit it and embed it on an annealing system, then you're fine. So that's what we will look at. But let's talk about this discreteness first. So what we see here is nothing to do with quantum computing for now. I just wanted to give you that sense and appreciation of the discreteness in quantum mechanics by looking at the quantum numbers. So if you want to describe an electron quantum mechanically, you have four quantum numbers that you can use. And all of these four quantum numbers are discrete, they're not continuous. So if we look at the first one, n, the principal quantum number, then this designates the principal electron shell. N describes the most probable distance of the electrons from the nucleus. And the larger the number n is, the farther the electron is from the nucleus. And the larger the size of the orbital, and the larger the atom is. So here on the right, these red bubbles that you can see here, these are the orbitals. So, and if we look at the number n equals 1, then you see a very small orbital, and n equals 2, it's bigger, and n equals 3, even bigger, and so on. And what this is a probability distribution. So where it's most likely that you find, most probable that you find the electron if you look for it. But you can see it's not, so if we look at 1 and 2 here, it's not that we have a continuous spectrum, it's really discrete. So there's this jump from 1 to 2 for the principal quantum number. If we look at the second one, the orbital angular momentum quantum number, called L here, that determines the shape of an orbital and let's say therefore the angular distribution. And the number of angular notes is equal to the value of the angular momentum quantum number L. So the value of L is dependent on the principal quantum number. So it's, in short, there is always a strong dependence of L from N. And unlike N, the value of L can be 0. So the principal quantum number cannot be 0, whereas the orbital angular momentum number can be 0. It can also be a positive integer, but it cannot be larger than 1, less the principal quantum number. So meaning n minus 1. So L can be 0, 1, 2, 3, and n minus 1. Okay? Then we have the magnetic quantum number, which is abbreviated m sub L. The magnetic quantum number m sub L determines the number of orbitals and their orientation within a subshell. Consequently, its value depends on the orbital angular momentum quantum number. And given a certain orbital angular momentum quantum number, the magnetic quantum number is an interval ranging from minus L to plus L. So it can either be 0, a negative integer, or a positive integer. Okay? And ms is the last one, so m sub s, the electron spin quantum number. Unlike the first three, unlike n, L, and m sub L, the electron spin quantum number m sub s does not depend on any other quantum number. So it designates the direction of the electron spin and may have a spin of plus 1/2, represented by an up arrow, or minus 1/2, very often represented by down arrow. So you will see these different kinds of notations quite often in quantum physics. And that means that when m sub s is positive, the electron has an upward spin, which can be referred to as spin up, and when it's negative, the electron has a downward spin, so it's spin down. And the significance of the electron spin quantum number is its determination of an atom's ability to generate a magnetic field or not. Okay? And now let's look at some examples. If you look at that slide for a moment and read through these examples. So if we look at the first one, N, if an electron jumped from an energy level N equals 5 to an energy level N equals 3, did absorption or emission of a photon occur? That's something that is very important when you want to add energy to that system. So elevate the electron by one level, so by one principal number, then you have to add that energy by adding a photon with a specific energy. And if you want to lower the electron, emission must happen. So in that case, that question, or the answer to that question is emission happened because energy is lost, and it's lost by the release of a photon. It's very important that for elevating an electron by one energy level, that photon must have exactly that energy of that specific level that you want to elevate to. Then let's look at the second example. If n equals 7, what are the possible values of L? So if we look at that, since L can be 0 or a positive integer less than n minus 1, then it can have values of 0, 1, 2, 3, 4, 5, or 6. So all of these are possible. The only thing it cannot be is 7 or more than 7. Yeah, so remember, L can be 0 to n minus 1. So let's look at the third one. If n, the principal quantum number, and n equals 3 and L equals 2, then what are the possible values of m sub L? So the possible values for m sub L, since they must range from minus L to plus L, can be anything from minus 2 to plus 2. So integers from minus 2 to plus 2. Minus 2, minus 1, 0, 1, 2. Okay? Now let's look at the last example, m sub s. List the possible combinations of all four quantum numbers when n equals 2, L equals 1, and ML equals 0. So that means the first, if we think about what we just talked before, the fourth quantum number is independent of the first three, allowing the first three quantum numbers of two electrons to be identical. And since the spin can be plus 1/2 or minus 1/2, there are two combinations. So for n equals 2, L equals 1, and ML equals 0, we can have spin quantum number plus 1/2, and we can have n equals 2, L equals 1, ML equals 0, and spin quantum number minus 1/2. So these are the two combinations that we see here. All right, I hope that gave you some brief overview on the discreteness of quantum physics. This is just so far an introduction to discuss some fundamentals and show you some fundamentals as to why quantum physics is discrete. This is, by the way, also a problem for gravity and trying to find a quantum theory for gravity. As you know, there are four fundamental forces in the universe, which is the weak interaction, responsible for some for radioactive decay. Then there is the strong interaction holding together our nuclei. There is the electromagnetic force, so light that we see and can measure. And then there is gravity. And for the first three, there is a quantum theory. For gravity, there is none so far. And so one of these problems is this discreteness. And if we visualize these electron orbitals, so looking at this picture that we see here, there are different ways to look at that, but this is one way to visualize them. And what this shows you is the most likely or the probabilities, where the probabilities are highest to find the electron when you look for it. So when you measure the system, or is it most likely to find these? And it's most likely to find them inside these orbitals that you can see here. And as you see, they become more complex. Um, the more complicated if we look at different combinations of quantum numbers here. Okay, now let's go or continue with the introduction to quantum computing. So first, what I have here is some breaking news, so some news articles that I looked up today and found. And so if you just look up Google and type quantum computing and look at the news, I'm sure you find some exciting stuff today too. But here, the first one that I found is AI and quantum computing to be the most impactful next generation technologies in defense. So I know that so specifically people in defense fear quantum computers. So this is one thing that we always have to keep in mind. Quantum computers can unfortunately not only be used for the good, so as with any other technology, there is the potential that people use it for the bad. And one thing that people are afraid of these days and will continue to be afraid of over the next couple of years is breaking encryption. We'll talk about that a little later, but so the premise here is that um, uh, current encryption algorithms that we use quite often to encrypt our internet-based communication, such as telebanking, even the communication between devices, such as vehicles, is prime factor based. So, for example, RSA, that's based on the premise that you cannot easily find the prime factors of a huge number with a quantum computer, which is how you create your keys. But with a classical computer, you cannot find this, and which is how we create your keys. And now with quantum computers, there's a very famous result from the 90s developed by Peter Shor. And with quantum computers, the promise is that you can do or find the prime factors of a big number efficiently. And this is something we have to worry about. This is something we have to worry about even today, because what that means is that potentially at some point in the future, someone will be able to crack our encryption algorithms that we use today. And one thing that we want to think about is not only about when it happens, about the point in time when it happens, but also what if someone steals our data today that's encrypted with today's algorithms, and in 10 years they're able to decrypt it? Is that still a problem for a company? And if it is a problem, then we have to think about how to prevent such attacks. And there are a couple of things that are interesting. It's post-quantum cryptography, quantum cryptography, which we'll talk about later too. But in short, so either you use algorithms that can theoretically withstand an attack of a perfect error-corrected quantum computer with a significant or sufficient number of quantum bits, or you use some quantum hardware to generate these keys. So that's also possible, so that there is no algorithm that can reproduce your key generation. And then the other news that I found today was Archer Materials shares rise after signing quantum computing agreement with IBM, which is also very interesting. So one promise of quantum computing is solving material science problems. So basically what you do is you take one quantum system, the quantum computer, and use it to simulate another quantum system, the molecule. And if we can do that efficiently, and if we can do that exactly, then so many things will change, so many benefits we will have. So for example, one thing that we're interested in is learning about electrochemistry in batteries. So how can we improve the electrochemistry, find new cathode or anode structures of batteries That's something that we're very interested in. So we want to improve the batteries, the capacity, we want to speed up the charging, we want to make them more durable. But there is many more things that we can envision. So one concept, a conceptual idea that exists and has existed for a while is space elevators. So what you do is basically you have a long rope and you have a lump at the end of this rope, specifically in geostationary orbit, about 35,000 kilometers from surface of Earth. And that rope holds that platform in geostationary orbit and it rotates with the Earth rotation. And so if you had such a structure in place, you could comfortably and cheaply transport materials to space, and you could use it as a launch pad for shuttles, for expeditions to the moon or to other planets in the solar system, or even beyond. But the problem is that with today's materials, we don't know any material that could, that has the tensile strength that's needed to build such a structure. So, but here the problem is again is if we have quantum computers that allow us to simulate um, molecules exactly and give us a way better understanding of materials than we have today. So instead of doing the approximations that we do today, really be able to simulate it exactly, that would be huge, and that will be huge. So it will happen, and this will change a lot too. But we'll talk about material science a little later. So now let's look at the very fundamentals of a quantum computer. So what is a quantum computer? It cannot be defined as a quantum computer or a computer that operates under the laws of quantum mechanics because your laptop does that too. So everything around us exhibits quantum effects, including your laptop, but it doesn't use these quantum effects to do computation. Um, so what we mean by that is its operations exploit special transformations of its internal state. So we really want to use quantum effects, and there are three specifically that are interesting that we will learn about. It's the superposition, it's entanglement, and it is tunneling. And depending on the architecture, we don't need all three, but depending on the architecture, sometimes we need three. So we'll see about and learn about that too. The difficulty with quantum computers is that you have to isolate it or isolate the qubits more specifically from their own irrelevant properties. So the system per se must be isolated. To give you an example, so many vendors today, so companies that manufacture quantum computers, they rely on superconducting qubits. And superconducting qubits means they have rings of metal, um, so either aluminum or niobium, and these rings that have to be, because they're superconductors, have to be cooled down to 15, 20 millikelvin. So it's very close to absolute zero. It's close, it's colder than space, so in space we have about 2.7 Kelvin. But if you think about how cold these qubits must be, so it's very close to absolute zero. So since they are superconductors, and once you cool them down to that temperature, you can induce current into these rings in both directions, which is not possible uh, in a metal at room temperature that is not a superconductor. So you can induce current in both directions, and what that creates you is two magnetic fields, one magnetic field up, one magnetic field down, and this is your qubit. But here you see the first challenge. You have to cool them down. So what that means is, while the chip is still the size of your thumbnail, you need a huge fridge around it that is capable of cooling that whole system down. So cooling the chip down over multiple stages to so close to absolute zero. That's one thing. The other thing is that you have to operate these quantum chips in a vacuum. Because if you have atoms flying around in there, so let's say you have an oxygen atom flying around, and all of a sudden it lands on the chip, it lands on one of these metal rings, one of these qubits, then it will hamper with your computation. So that already disturbs the computation. So you see um, how careful you have to be here, and that's what is meant with isolating these systems from
the environment and also their own irrelevant properties. And the third one is the superconductors, since they are magnetic qubits, the superconductors, they are very sensitive to magnetic interactions. So the Earth magnetic field is too strong. It will negatively influence your computation. So what you have to do is you have to shield the Earth magnetic field from your quantum computer as good as you can if it's a superconducting qubit chip. So you see, you have three challenges with this specific architecture, and there are other challenges with other architectures because all of these systems are very sensitive to environmental noise, even to their own noise. And so this is something that makes it even more difficult to engineer, to build these systems. So you see here in that slide on the bottom, I have, if you can't do it, you have decoherence. So in decoherence, and we'll learn about what that means in more detail, but that just means this superposition that we will also learn about is one of the quantum effects is lost. So the system will collapse from a rich state of encoding many different solutions to a problem, ideally, to only one state, giving you one potential solution to a problem. And if you don't do that right, then you'll not do any good. You won't get the solution that you want. You won't get the solution to the problem that you need. But again, we'll talk about this in a bit. Um, so what's more, qubits cannot be encoded in systems of macroscopic size. As such, cannot be isolated from its irrelevant properties. So again, this is the same problem that we had before. So you really have to think about how to isolate the quantum effects that you need for your computation from the rest of the environment. So isolation in that case can be achieved if qubits are encoded in a small number of states of a system of atomic size, or extra internal features do not matter because such do not exist or require unavailably high energy to come into play. And such systems must be decoupled from their surroundings except the completely controlled interaction that are associated with the computational process itself. In terms of avoiding decoherence, so we only encode a small number of states in these systems of atomic sizes. Um, we isolate these systems as good as we can. So, like I mentioned before, for example, shielding from the Earth magnetic field, but it's definitely not hopeless. So it's possible, and we've seen these things can work. It's just incredibly difficult to build these systems, but as we move forward in time, we'll learn about more. Um, we learn more about how to engineer these systems and improve these systems. Okay, so then we have to do quantum error correction, which is also a very challenging task because we need to do a correction without knowing the original or corrupted state. So you see, this is another challenge on top. Error correction comes into play when, so for example, let's think about superconducting qubits again. So a measure of quality for superconducting qubits is called fidelity. So fidelity expresses the probability that, for example, a two qubit operation, so an operation that you conduct on two qubits, um, gives you the right result, gives you the result that you expect. So let's say you have a fidelity of 99%. That sounds really great. But if you have 1 million qubits, then it's not so great at all because this error, it will, so to say, propagate through the chip. And in the end, you will still have random results, although for two qubit operation, for a single two qubit operation, the fidelity is 99%. So there are ways. So let me go back to that. Why it happens? So it happens because materials are not perfect, and you still have interactions with the environment. So sometimes it may just happen that a qubit flips. There's a bit flip that happens, and ideally you want to avoid that, but you can't because there are as I said, problems with the materials that we use for these systems, so they're not perfect, and some other problems that we can think of. So we need algorithms for doing the error correction in the end. But you do that once you get the result. So ideally, you have to understand your chip really well to be able to implement an error correction algorithm that's suitable for that chip. But we'll get to that too later. And why quantum computers at all? Because the hope is that we can do things more efficiently with quantum computers that we can do with classical ones. And there's proof already. Google, for example, did a great experiment 2 years ago, a quantum supremacy experiment, where they show they can do um, something with a quantum computer that a classical computer cannot do. So right now, this doesn't mean that for practical problems we're there already. So now we're in this regime of the NISQ devices, which is the abbreviation for near intermediate scale quantum devices. And over the next couple of years, so let's say maybe 5, 7 years, we will be in that NISQ era. And in that NISQ era, we will most likely not be able to solve practical problems that a classical computer cannot solve at all, but we will be able, and we are already able, to solve practical problems faster than with with classical computers. And if you can do that, that can already be a significant advantage. So let's say we talk about a practical example, traffic flow optimization. If I can calculate the optimal distribution of vehicles faster, let's say only 5 or 10 minutes faster than a classical computer, then this can already be a significant advantage for my business or for the solution that I want to develop. So here on the bottom right on that slide, you see an example. So where you have the classical computation time, so the classical computer always increasing so exponentially with the input size. With a quantum computer, the premise is that we linearly increase the computation time instead of exponentially, so with the input size. So we should still be fast, even though with classical, we should be fast even though the size of the input grows. So if we look at that now, the history of computing, and I'm sure since you here at the Leiden Institute of Advanced Computer Science, you know all that, but still let me repeat it. We talk about the history of computers, so we have to start talking about Babbage. So he invented something called the difference engine, which is an automatic mechanical calculator, and was designed to tabulate polynomial functions. So it was purely mechanical, which is really impressive, and that's how that whole field started. So the next person of interest and made great contributions is Ada Lovelace. So you could say she invented software and the first computer algorithm that computes Bernoulli numbers, which is really interesting. So the Bernoulli numbers, by the way, are a sequence of rational numbers that have deep connections to number theory, which was pretty interesting too. Then another big name in computer science history or history of computer science is Alan Turing. And as you know, he invented the Turing machine. So a Turing machine, if you remember correctly, is a very abstract machine that manipulates symbols on a strip tape according to a table of rules. Or more exactly, it's a mathematical model of computation that defines such a device. And despite this model's simplicity, given any computer algorithm, a Turing machine can be constructed that is capable of simulating that algorithm's logic. Yeah, and so it also makes sense to talk about the Entscheidungsproblem in that context, which is, so the Entscheidungsproblem asks for an algorithm that takes as input a statement of first order logic, potentially or possibly with a finite number of axioms beyond the usual axioms of first order logic, and simply asks answer is yes or no, according to whether the statement is universally valid or not. Valid in every structure satisfying these axioms. And that's where the Turing machine comes important again. And now if we look at classical computing devices, so you see um, the abacus on the top left here. So one of the older devices here on the bottom right, you see silicon chip and also transistors here. And then it's very important to talk about Richard Feynman, because Richard Feynman, he kicked the whole field of quantum computing off. And it was, if I remember correctly, in 1982 when he asked that question. So he not specifically asked it how I give it to you now, but he was asking that question that, so if you think about simulating quantum mechanical systems with a classical computer, he was wondering why that is so difficult. And the question that he asked was, does that mean that if we use quantum effects for computation, that such computers are more powerful than classical computers? And that kicked the whole field off, and people started thinking about it. So, by the way, a very interesting um, publication here to look into the quantum Turing machine here. And you see, so this one was authored, so quantum theory, Church-Turing principle, universal quantum computer down here was authored by David Deutsch. And David Deutsch was the guy who came up with Deutsch's algorithm. So he found out, or he could show, that if you want to find out if a function or a set of functions taking um, input of bits, if let's say you have four functions, you can find out if this set of functions is constant or balanced using a quantum computer more efficiently than a classical computer. We'll look at this algorithm specifically later. So then Simon's algorithm, also very famous. It's a special case of the abelian hidden subgroup problem. Then you have Shor, who came up with the Shor's algorithm. So it could show that with so a quantum classical algorithm, it's always very important to mention that this algorithm is not purely quantum. But with a quantum classical algorithm, you could solve the factorization problem efficiently. And then there is Love Grover, who in 1996 came up with an algorithm for search. This is somehow misleading if we look at how it's generally specified as a search in an unsorted database with n entries. It really means that we have a function inverter. So that's more accurate if we talk about a function inverter. But anyway, so the solutions, so let's say you have 1 million entries, then in square root of n time, you will find your, with square root of n queries, you will find your answer. So which in that case would be 1000. Worst case scenario for a classical algorithm, and we always think about the worst case scenario, is 1 million queries. So if you want to find one specific entry. So that's a significant improvement compared to classical machines. And so if we look at ways of implementing quantum computers, or different ways of implementing quantum computers, there are photonic or optical quantum computers, then quantum dots, which are quantum particles that we can use for implementing quantum bits. Then the flux quantization, which are the magnetic quantum bits that we briefly talked about before already. So abbreviated SQUID, superconducting quantum interference device. And also liquid state nuclear magnetic resonance. That's another way of implementing it. And so most promising these days are superconductors and ion traps. There's another very interesting publication to look into, released in 1998, and it's quantum annealing. So quantum annealing is that other architecture that we will learn and talk about that can be used for solving optimization problems and sampling tasks. It's very interesting, but I recommend reading that publication. So there's a lot that happened in that field since 1998, but Still, this one is particularly interesting and kicked the whole field of quantum annealing off. Another interesting thing, just to give you uh, some overview about how competitive the field is. There was this publication by IBM in 2015 that said there are three types of quantum computers, and one of the quantum computers that they have is a quantum annealing, or that they described here as a quantum annealing system, and they described it as the least powerful system, and that was published on December 7, 2015. And interestingly, on December 8, 2015, Google published some results using D-Wave's quantum annealing system, and they said for comparing it with simulated annealing is more than 10 to the 8 times faster than simulated annealing running on a single core. So that's very interesting too, but then that raises another question already. So it's a good result. You can see that comparing one chip to another chip, so one chip, a classical one, to a quantum annealing system, um, is an interesting point already, and shows that for certain problems with a quantum annealer, you can be faster. And then this other question that we always have to think about is, what do you compare a quantum computer with? Do you compare it with one chip? Do you compare it with a supercomputer? Do you compare it with, so whatever you use, what is the right thing? So it's not that simple. You cannot just say I take one quantum chip and compare it to the fastest classical chip, because the expectation that we have is that at some point one quantum chip will beat no matter how many classical chips I have in my supercomputer. So this one chip will beat all of them. So this is the expectation that we have. So even if that is an interesting result and was funny that it was just published one day after IBM announced that quantum annealing systems are not powerful and very restricted, that Google said they see it differently. Anyway, so if we continue with the historical observation, and how quantum computing and computing in general um, uh, was kicked off, then it's always the same, right? So it's mankind develops new models of physical phenomenon, and then we employ devices or develop devices employing this physical phenomenon. And sometimes the model comes first, and sometimes the device comes first. And I added some examples here um, that um, always ended up. So we have a hardware device on the left, and you have the model on the right. Summing up, we have developed excellent models of quantum phenomena. If these are the right models, we don't know yet. An interesting question to ask is always, so we'll see that the language of quantum physics is linear algebra, but nothing in real life is linear, right? So it's an interesting question, but it's the best model that we have describing nature as we observe it from experiment, as we learn from it from experiment. And devices making use of these models are widespread. For example, transistors. So D-Wave is one company, was the first to market with a quantum computer years ago already. I don't know exactly when, but I think before 2010 even, they had a quantum computer available to industry customers if they wanted. And they do adiabatic quantum annealing, so it's the special purpose quantum computer. And many more institutions, not only recently started working on quantum computing, including but not only Microsoft, Intel, IBM, Google. Many academic institutions are exploring alternate quantum computing models. And as I said, the universal quantum computer is the one that we all want to have, and at some point we'll have it. So the universal quantum computer that allows us to solve industry relevant problems or problems that are relevant for humanity. The interesting and so I would say the most important thing that I want to give you, or I want to conclude the lecture with today, is that quantum computing is here now. Quantum computers are available. You can solve industry relevant problems with certain kinds of quantum computers today already. is definitely worth looking into quantum computing today, and the talent is rare. So people being able to do quantum computing, you don't find too many out there. So it's good that you're in this course, and I'm sure if you want to work in that field, if you find that exciting, you won't have any problems finding a job. It will become more and more important over the next years. Thank you very much for your attention, and looking forward to the next lecture. Have a good remaining day.